Good afternoon. I'm here to present our work titled Establishing Baselines for Dyadic Visual Motion Prediction using the QUB-PHEO datasets. I'm Dr. Samuel Adebayo and my co-author is Professor Sean McClune. So dyadic interaction essentially means reciprocal. So it is a two-way exchange between two agents. And when we talk about agents, we're referring to a human or a robot. And because it's two-way, it could be between human and robot, or it could be between human and human. And this often involves several stages, as you can see from our figure here, that this stage, the first stage of dyadic interaction is perception and detection. This would involve having to know what the human is currently doing, which is detecting the task at hand. And then, of course, intention inference, which is our primary focus in this research, followed by contextual understanding, trying to understand the context of the interaction. And of course, you would want to ensure safety and ethical consideration put into place, and of course, decision making and action execution. And given that our research is mainly focused on collaborative assembly, the sources of this dyadic interaction or any form of dyadic interaction at all would often depend on tight temporal and spatial coordination and communication, and this sort of communication could be via verbal communication or non-verbal cues. Extensive research has been done in the area of verbal communication, especially when it has to do with two-way communication in human-robot interaction or even human-to-human interaction. Now, given this, that for us to be able to achieve a very good dyadic interaction, one of the stages, which is intention inference. And when we talk about intention inference, it means to anticipate for near future actions, because we would want the robots, when interacting with humans in the future, to be able to infer and know exactly what the human is about to do even before they do them. So, which means this is going to be central to proactive, including safe interaction and safe collaboration. And that brings us to the idea of short horizon motion prediction, which is obviously a practical route to intention inference. However, in this particular space, in the space of in human intention inference, in a human to robot interaction, the progress comparison have been had, and especially when you compare to interaction or intention inference based on verbal cues, and when you compare that to non-verbal cues, the progress is quite hard, and it's currently limited. So, and the reason for this is because due to heterogeneous data sets, and there are no set metrics in this particular space, which is what our research is trying to address. Now, because our research is in the area of dyadic human-robot interaction, we're focusing on the use of non-verbal cues. And non-verbal cue-based dyadic interaction depend on cues such as gaze, gestures, body motion to essentially foster trust and collaboration. It's just like when you communicate between another human, you're able to understand what they're doing based on their gaze, their body motion and gestures, and the way they move their hand and talk when they communicate with you. Same way, if you look at when you communicate with a robot or you interact with a robot, you would want to use the same input and the same gestures and the same non-verbal cues essentially to infer intention. So that means that intention inference via short horizon motion prediction would help robots anticipate actions and coordinate smoothly. And just to quickly say that when we talk about short horizon motion prediction, we're talking about a motion prediction which is an estimate of an agent's immediate future direction. This often involves between 1 to 2 seconds, being able to predict what that is going to look like based on recent observation. And this would obviously emphasize any sort of near-term kinematics, the way your motion and the body moves and all sort of things. It could either be predicting the gaze or could be predicting where the hand is going to be in the next 1 or 2 seconds. So this means that diverse datasets and unified evaluation protocols are really essential to compare models and drive progress in this particular space. But then you may ask, why do we care? Why do we have to do this? And the reason for this is that nonverbal cues are essentially going to boost efficiency and safety and trust in collaborative tasks, because that way the robot can understand humans better. And without context awareness, especially because one of the core stages of dyadic interaction is context awareness, so which means without this, robots cannot really plan proactively. So given all these observations, our goal is to predict human hand trajectories 2 seconds into the future, given the past 2 seconds of motion in collaborative assembly tasks. So first, our contribution number 1 is we establish a reproducible baseline benchmark for dyadic visual motion prediction on QUB-PHEO fixed data sets, and we came up with a subject-head out split and hand-centered normalizations, metrics, and full training and evaluation script, and then we release the code and splits and weight as a starting point into this research space. And then we established baseline results across 5 neural network backbones. Under 3 input regimes, we have 84-dimension hands only, and 94-dimension hands, surrogate, and gaze, more on this later, and 214-dimension full area context. This helps us to review the robustness hierarchies beyond deadline accuracy and to serve as a starting point for those who want to explore research in this particular space. And finally, we also looked at providing a sort of a yardstick. This research present a yardstick for the dyadic HRI community, such that it's going to be a starting point and a like-for-like comparison and easy extension to new models and modalities. The QUB-PHEO datasets. QUB-PHEO means Queen's University Belfast Perception of Human Engagement in Assembly Operation. Contains 70 participants involved, over 36 hours of dyadic in assembly operations, and we had 36 subtasks as well, covering different pick and plays, tool handovers, and joint manipulations. And we had 5 synchronized camera views, 4 side view cameras, and 1 area view. You can see the setup of our cameras below on the right hand side of the slide. During every data recording session, we calibrate the cameras to ensure we have the correct parameters. So in addition to having 5 synchronized camera views, we also had rich annotation. We annotated the data set to have 2D hand key points. We extracted this from different views, and the robot surrogate hand bounding boxes, gaze endpoints, and even up to 30 object bounding boxes. As you can see on the right hand side, the plots of our data sets and different views as well. So our data set paper was published in the IEEE Access paper 2024. Please do check it out for more details. So the methods. The goal here is to have a short reproducible short horizon motion prediction, which is essentially to predict 2 seconds future hand trajectories from the past 2 seconds of operation in a dyadic assembly operation. And the whole pipeline here is that we have data, which is the QUB-PHEO data sets. We pre-process that, now normalized, and then we do a bit of windowing so that we know from what point to what point are we trying to extract and get, and then we encode the input, which is so that we have a normalized and encoded input into the data, into the model. And then of course we came up with different models and then computed the laws and then the metrics, and then we came up with the analysis, which we're going to talk about in a few moments. And the scope here is to have a reproducible baselines on QUB-PHEO with fixed plates, code, and weights, so that there is a starting point and a baseline for people who want to be involved in this research. Methods, preprocessing, and input. So we use a windowing to sample the data. So from our paper, we use 60 frame observation window and a 60 frame prediction horizon, which correspond to 2 seconds of data. We had to resample the data to 30 frames per second for normalization so that we have equal frames across board. And we use a stride of 15 across each of our subtask clip, and we use a subject held out split at 60 Hz. This corresponds to essentially 1 second. For our input regime, we use and for fair comparison essentially, and to see how the models are going to perform when the input modality is different, we have a regime for hands only, which means we fed the model hands only data. This corresponds to 84 dimension, and we also did for hands plus surrogate plus gaze, and when you add all of those together you have 94 dimension. And then for the full area context, which in this case involves the hands plus the surrogate plus the gaze plus the object bounding boxes, we had 214 dimension. And then we took all of these and fed them to the model. For the model side of things, we considered 5 neural networks: TCN, Bi-LSTM, Bi-GRU, and Transformer and ST-GCN. And all of the models share the same heads, outputting essentially 60 key points dimensions. So quickly, I'll talk about the architecture of these models. So for the Bi-LSTM, we use 2 stacked bidirectional LSTM layers with a hidden size of 128, and we use tan H as our gates, and then obviously a fully connected projection with a ReLU activation layer and a dropout of 0.1 between all of the layers. For the Bi-GRU, we use identical topology, but GRU cells, and then we use the ReLU applied to each of the time step. And as for the temporal convolutional neural network, TCN, we use 4 one-dimensional dilated convolution blocks with kernel 3 and dilations of 1, 2, 4, and 8, and 128 channels. So we also applied the ReLU activation function, and then we did layer normalization with residual connections throughout. As for the transformer encoder, we use 6 layers and a width of 128 with 8 Hz, feed-forward dimension of 512 with a ReLU activation function. We also use a dropout of 0.1 with sinusoidal positional encoding. For the spatial graph, we use 42 and key points and joints because it's a spatial graph-based neural network with 3 ST-GCN blocks. Essentially, we had channels of 64 to 128 to 256 with temporal kernel of 9, and we use a p-ReLU after each of the block. Now, for all of the models that we use and the backbones that we use, they all have at the very end point a pose head, which is a multi-layer perceptron of input into that of 256 and a hidden layer of 512 with a ReLU activation function and an output layer of 84 or 94, or as the case may be 214 dimension. So with that said, for the loss, we use a normal mean squared error loss. And for the metrics, we use the MPJPE and the ADE and FDE, in this case, average displacement error, which is essentially average L2 distance across all predicted frames. And FDE, in this case, is final displacement error. All of these metrics are in 2D, not in 3D. We'll present the results. So we trained all of the models on the following input regimes, and only Hands+surrogate+gaze, and then the full area input. And all of the errors reported here normalized 2D units, which means they are scale free, and the pixel values are available by rescaling with stored per sequence calibration available in the repository for this paper. So based on this, for the hands-only results, the temporal convolution neural network achieves the lowest error,
which is 0.763. Bi-LSTM follows closely with 0.912 MPJPE, while Bi-GRU and transformer underperform. The ST-GCN fails woefully due to the graph constraints in this case, because obviously we're using hands only, so we expected that the results would be like that. Now, for the hands and surrogate plus gaze input regime, the Bi-LSTM in this case improves dramatically to 0.681 MPJE. TCN, GRU, and transformer, they degrade, and this signals difficulty in fusing surrogate and gaze cues. The ST-GCN diverges when folding modalities into its graph, as you can see in this plot here, that ST-GCN still perform really woeful. And then for the full area input, in this case, we fused all of the inputs together, which means we have more inputs. So in this case, the TCN regains its dominance with 0.796 MPJPE. Exploring object context in this case, because now we've added the objects to the input regime, and Bi-LSTM degrades to 1.197, and GRU and transformer remain high. The ST-GCN still fails, which means it reveals to us that there is a need for modality-aware graphs. So based on these results, we present our observations from the baselines. Across all of the regimes, robustness hierarchy, we can see that TCN performs better compared to Bi-LSTM and all the other architecture. And for the hands only, TCN is the best. And for hands and surrogate plus gaze, we can see that Bi-LSTM becomes the best. And this can be seen because sequence models benefit from attention cues. In this case, we've added gaze and surrogate hands. But TCN degrades, which obviously would indicate sensitivity to heterogeneous features without modality-aware designs. On the other hand, the full area context here, which involves all of the input modalities, we have 214 dimensions. The TCN regains its best position, while Bi-LSTM degrades. So given this, we can observe that based on the architecture, that robust temporal filters such as dilated conv, as we can see in TCN, are key for keypoint-based short horizon motion prediction in HRI. And this also means that effective fusion of heterogeneous cues requires modality-aware designs. You can't just fuse them all together. There has to be a way to do that. And the ST-GCN needs a redesigned graph topology to handle extra modalities. As you can see, its performance was woeful all through. So there are several failure modes and implications, as we can observe that ST-GCN diverges with extra modalities. As you keep adding more inputs, it keeps diverging. So which means for future work, modality-aware fusion would be required, or a graph redesign and regularization around the 214 input dimension. So based on this, our future work would focus on fusion, modality aware for hands, the gaze, objects, and maybe also to redesign ST-GCN with type edges, and also maybe supervision around multi-view 3D hand labels, maybe to use the frames, not just the key points. And also longer horizons, maybe not just 2 seconds, we would also consider 4 to 6 seconds, robustness suits, and maybe to add more reliability metrics. So we call on the research community to use our repository and to use our data sets that we have available. If you have any question, please do not hesitate to contact me via this email, and our repository is on GitHub. Please do check it out. Thank you very much.